Well, section 6 discusses determinants and their properties. It's a short section, but it's important because the determinant enters in the computation of the eigenvalues, and knowing the properties of determinants might help you to compute determinants efficiently, so that you can efficiently compute the eigenvalues. Well, the determinant can be computed for a square matrix, and it's a single number that packs quite a lot of information about the matrix, so you can tell immediately if the matrix has an inverse. If the matrix is singular, it has no inverse, then the determinant will be 0. You might know from other courses or previous courses that determinants enter in formula of the inverse of A and the solution of AX equals B. Okay, but for large matrices, okay, you should not use this formula to compute the inverse of A or the solution of AX equals B. You should use the methods that have been proposed. So for the inverse of A, you put the identity matrix next to it so that you obtain an augmented form, and then you do Gauss-Jordan elimination. And for the solution of AX equals B, you do just Gauss elimination. You bring the system in upper triangular form, and then you do back substitution. These are the methods that are by far the most efficient methods, so that you should not forget. So we'll talk about the determinant of the matrix A, okay, and we'll do this in 3 ways. We'll obtain a so-called pivot formula. Well, this is the most efficient way to compute the determinant. There will be a so-called big formula. Well, you'll have lots of terms, n factorial terms, and well, there is also the well-known cofactor formula that we'll talk about later on in the course. The determinant of a matrix is either denoted like this or like this, and this is here the preferred notation. What is amazing is that the determinant follows from only 3 rules. Okay, we'll talk about these later. And all the other rules and the computational formula, well, they follow from these rules 1, 2, 3. Okay, so let's start with the first rule, which simply says that the determinant of an identity matrix of dimension n is 1. The second rule says if you take a matrix and you interchange 2 rows, then the determinant will change sign. So let's apply this. We have just seen that the determinant of an identity matrix is 1. So if we interchange rows 1 and 2, we obtain this matrix over here, and this matrix will have determinant -1. Then there's a third rule, which might maybe ask for a little explanation in the next slide. The determinant is a linear function of each row separately, and this rule only applies when the other rows do not change. So here we show what we mean by linearity of each row separately in a 2x2 example, and we apply this linearity for row 1, okay, and row 2 stays the same. You notice that C and D are always the same in each of these determinants. Well, this linearity of each row separately says that if you multiply a row by a scalar, okay, as is done over here, you simply multiply the determinant by this scalar. Okay, so here we have a row of A, and that is added on top of a row of A prime. So we've got this determinant to compute, and linearity of each row separately simply says, well, you can see this as the sum of two determinants, okay, the one with the initial row and the other one with the new row. And in both determinants, well, of course the second row remains the same. Okay, remember that we had that the determinant of an identity matrix is 1. Okay, it's an identity matrix of dimension n here, but the determinant of 2 times the identity matrix of dimension n will be 2 to the power n. Let's take an example. So E3 is 1, 1, 1. 2 times E3, well, it's 2, 2, 2. So if we take the determinant of 2 times E3, it's the determinant of this one. So by this property we can say that it's 2 times this determinant. It is 4 times this determinant. And it is 8 times, but 8 is also 2 to the 3rd power, this determinant here, 1, 1, 0, 0, 0, 0, 0, 0, and this is 1. Okay, what we have done here is applied this rule for each of the rows. Well, we'll use these 3 first rules to obtain 7 more rules, and these rules make determinants much easier to work with. So the first extra rule is, if 2 rows of a matrix are equal, then the determinant of that matrix is 0. Obviously, if 2 rows of a matrix are the same, if you interchange these rows, the matrix is going to stay the same. Okay, so we expect the determinant to stay the same. But rule 2 says, well, you have exchanged rows, so you should have a change in sign. The only way that you can have an identical determinant and that the change of sign is applied is if this determinant is equal to 0. Well, the 5th rule says that subtracting a multiple from one row to another row leaves the determinant unchanged, and this can easily be seen as you take an example. So what we have done here, we have subtracted L times row 1 from row 2, and what you can do is, using this linearity property for the second row here, we can say this is this determinant, okay, minus L times this determinant. Okay, so in the original row we had C and D, and what we have subtracted is the rows A and B. So this is linearity, one row at a time, and it corresponds to row 2. But here we have a determinant with 2 identical rows, so this is a 0 determinant. So we have just proven that indeed subtracting a row from another row will leave the determinant unchanged. This is something that we can use to our advantage to obtain an equivalent determinant that is easier to work with because we have more zeros. Well, a matrix with 0 rows has a 0 determinant. Well, you can prove that by simply adding another row on top of the 0 row. By rule 5, the determinant is unchanged, and the matrix has now 2 identical rows. By rule 4, the determinant is 0. Well, rule 7 that we have to prove is that the determinant of a triangular matrix is the product of the diagonal elements. Okay, so we'll assume first that all the diagonal elements are non-zero, and what we can do is eliminate the off-diagonal entries to produce a diagonal matrix. We know that if we do elimination by creating zeros in the off-diagonal matrix, we will not change the value of the determinant. Okay, so what we can then do by rule 3, linearity per row, is to factor out each of the elements on the diagonal, and then we have that the determinant is the product of the diagonal elements times the determinant of an identity matrix, which is 1 by rule 1. Suppose that the diagonal or at least one diagonal element is 0, then the elimination procedure will produce a 0 row, and then we know that the determinant is equal to 0 by rule 6. Well, rule 8 says that if A is singular, then its determinant is 0, and if it's non-singular, if it's invertible, then its determinant is different from 0. Rule 8 will also lead to the pivot determinant formula, which says that the determinant of a matrix is the product of its pivots, and there could be a change of sign. Okay, and I'll talk about that later. First, how are we going to prove this? Well, we're going to use elimination to go from the matrix A to the matrix U, and we know, since we are using elimination, that the determinant of A will be the determinant of U. U is upper triangular, so if A is singular, well, U will have a 0 row, and we know that the determinant of U will be 0, so the determinant of A will be 0 as well. If A is invertible, then U will have non-zero pivot along its diagonal. So the determinant of U by rule 7 will be the product of its pivots, and that will also be the determinant of A. Since the pivots are all different from 0, the determinant will be different from 0. So we have also shown that the determinant of A is the product of the pivots. So why might there be a change of sign? Well, you know that in order to go from A to U, there might be a row change if you get stuck in the elimination procedure, right? So the change of sign will depend if the number of row changes is even or odd. If it's even, you have a plus. If it's odd, you have a minus sign. Well, rule 9 we will not prove, we'll just give an idea of a proof. The determinant of the product AB is the product of the determinants of A and B. Well, if you divide by the determinant of B, you have the determinant of A. So the idea is that the determinant of AB divided by the determinant of B should have the same basic 3 properties that define the determinant of A. And these 3 properties are, of course, rule 1, 2, and 3. So this is how you can prove this property over here. This allows you to obtain the determinant of the inverse of a matrix. Okay, so this rule over here says that the determinant of A times A minus 1, which is the identity matrix, is equal to 1. It's equal to the determinant of A times the determinant of A minus 1. So this shows that the determinant of A minus 1 is 1 over the determinant of A. Well, rule 10 says that the determinant of A transpose is the determinant of A. So A transpose determinant is the determinant of A. When A is singular, well, its determinant is 0. Its transpose will be singular as well, so that determinant will be 0 as well. So the proof is obvious. Okay, so what we'll do is the LU decomposition, or the PA is equal to LU decomposition, because you know that sometimes you have to exchange rows, and this explains the permutation matrix that you have over here. If you take the transpose on both sides, you remember that AB transpose is equal to B transpose A transpose. You obtain over this over here. L, it's a lower triangular matrix, so its determinant is the product of the elements on the diagonal, but the elements of the diagonal are 1, so the two determinants are equal to 1, and we know that this relation holds, okay, because of course the elements on the diagonal, if you take their product, will give you the determinant of U, but this will also be the determinant of U transpose. This one will be upper triangular and this one lower triangular. Okay, so we start from this equation over here. We know that the determinant of AB is equal to the determinant of A times the determinant of B. Okay, so from this equation we know that the determinant of P times the determinant of A is equal to the determinant of L times the determinant of U. This is a 1 over here, so this leaves us with the determinant of U. This is the determinant of U transpose. Okay, this one is equal to 1, so we can multiply. Okay, this is also a 1 over here, and using this relation here we show that this must also be equal to the determinant of A transpose and the determinant of P transpose. Permutation matrices are such that P transpose P is equal to the identity matrix, and they are orthogonal. So this means that the products of the determinant of P transpose times the determinant of P must be 1. This means that since they are permutation matrices, right, they are the identity matrix with rows interchanged, that both P transpose and P must either have a determinant that is 1 or minus 1, but in any case P transpose determinant is equal to the determinant of P. So we can cancel out over here, and we have indeed shown that the determinant of A transpose is equal to the determinant of A. Well, this rule 10 is a very important rule, right? Because it says that every rule that applies for the rows also applies for the columns, and you can obtain the result by just transposing, because we know that the determinant of A transpose is equal to the determinant of A. So the determinant changes sign when you interchange two columns of a matrix. When you have a matrix with a 0 column or two equal columns, its determinant is 0. If a column of a matrix is multiplied by a scalar, so is the determinant, and the determinant is a linear function of each column separately. Well, it's now time to find formulas to compute the determinant, and we had already found the pivot determinant formula, which says that the determinant of A is simply the product of the pivots, but you might have to change the sign because you might have to interchange rows when you compute the pivots, and depending on whether this number of row changes is even or odd, well, you will have a plus sign or a minus sign. Okay, so this pivot formula is very efficient when it comes to computing. Okay, so there is no formula that is more efficient than this formula. Of course, with this formula you cannot write the determinant in terms of the original Aij, okay, whereas with the cofactor formula it will be possible, but from a computational point of view this cofactor formula makes no sense. This one is much more efficient. Well, the big formula is obtained using rule 3, linearity of each row separately, and you applied it several times. You'll be able to split the determinant in n to the power n terms, and a lot of these terms will be 0, and you'll end up in the end with n factorial terms that are different from 0. So we'll investigate this for a 3 by 3 matrix, and we'll end up with, well, 3 factorial, that's 6 terms. Okay, so here we apply linearity for the first row. Okay, so we obtain 3 terms over here. We'll split the first one here in blue using linearity applied to the second row. Okay, so again we have 3 terms, and this one you can see that it is 0 because it's a lower triangular matrix, and on the diagonal you have a 0 element, so the determinant is 0. We take this one and we apply linearity for the third row. Okay, and again we obtain 2 determinants that are 0, same reason as before, lower triangular matrix, a 0 on the diagonal here and a 0 on the diagonal over here. So this one here is equal to this determinant over here. This one over here will also give 1 determinant, and so there will be 2 terms coming from this one. There will be 2 additional terms coming from this one, and 2 additional terms coming from this one. So this leaves us with n factorial, 3 factorial here, 6 terms for the 3 by 3 matrix. Well, as I said, this determinant, because of this third rule, right, linearity with respect to each row separately, well, it will lead to the sum of 6 determinants that are non-zero. This one is very easy to compute. It's a diagonal matrix, so you just have to take the diagonal elements and take the product. Okay, so this corresponds to this term over here. Here you have to switch this row and then switch these 2 rows, and you obtain a diagonal matrix A31, A12, and A23. Okay, so the determinant of that is this thing over here, and since you have switched 2 rows, well, the sign is a plus. So here you have to switch this row and this row to obtain a diagonal matrix. Then you take the product of the elements, and since you have switched 1 row, you have to put a minus sign. Okay, so this was rule 2. So this one here corresponds to this term over here, and in the end you obtain this formula over here. Notice that these 6 terms are such that there are non-zero terms that are coming from different columns and different rows. In each determinant, okay, you have 1 element per column or per row. You can also see that all these terms over here, they are such that the first element is always 1, 2, 3. See, 1, 2, 3, 1, 2, 3, whereas the second index, well, it's a permutation of 1, 2, 3. So here you have 1, 2, 3. Here you have another permutation, 2, 3, 1. Okay, and it's a permutation from 1, 2, 3. So in order to obtain this, well, you first maybe do 3, 2, 1. Okay, you switch this one, and then you have to do this permutation over here to obtain 2, 3, 1. 2 permutations, and it's a plus sign. Okay, so here you have another permutation, 1, 3, 2. Okay, 1, 3, 2, and this is obtained from 1, 2, 3 by switching the second and the third. So it's just one permutation, so it's a minus sign over here. Well, you can see that there are 3 terms that are positive and 3 terms that are negative, and this has led to the so-called Sarrus rule to compute a determinant for a 3 by 3 matrix. Well, the Sarrus rule is a mnemonic rule, so either you put the 2 first rows below the matrix, or you write the 2 first columns to the right of the matrix. Okay, and then you can construct the positive terms as shown, and the positive terms are the product of the elements of the diagonals that are in blue, and then the 3 negative terms are constructed from the products of the elements in the red diagonals. Okay, well, you sometimes wonder why this rule is thought, because, well, it works for 3 by 3 matrices, and then it has no easy extension to higher order matrices. I will show you that it's possible to extend it to 4 by 4, but it's very complicated. So I would forget about this Sarrus rule and stick to determinants being computed either by the cofactor formula or the pivot formula. Well, indeed, there is a generalization to 4 by 4. I could not find anything for 5 by 5 or higher. Okay, but you see that it is rather complicated. So we have 4 factorial, which is 24 terms. 8 terms are given by this array. So you take the matrix and you copy the 3 first columns to the right. Then 8 more terms come from this array where you have to switch columns, and then 8 more terms come from this array where you have again to switch columns. So 12 of the terms come with a positive sign, they are the blue diagonals, and 12 of the terms come with a negative signs. Well, they correspond to the diagonals in red. I hope you're convinced now that you should not use the Sarrus rule, not in the 3 by 3 case, and certainly not in the 4 by 4 case. So I don't want to see it anywhere in your exercises or at the exam. So please use the cofactor formula or the pivot formula. So what we've been doing for 3 by 3 matrices holds also for n by n matrices, and this will lead to a sum of n factorial elements. In this sum, well, you'll always have a product of elements of the matrix. So the index here will be I, right, and I will go from 1 to n, and the second index will correspond to the permutation of the original sequence that you had. Each permutation comes with a sign. Well, the sign is positive if you obtain your permutation after an even number of permutations of the original set, and it's a negative sign if it's an uneven number of permutations. Okay, so let's take an example where n is equal to 3. Okay, so this is my permutation here. Okay, so I will have a1, a2, a3. Okay, this comes from this index. Sigma 1 over here, it's 2. Sigma 2 is 3, and sigma 3 is 1. Okay, so which sign do we need to take? Well, in order to go from this one to this one, we need 2 permutations, so it's a plus over here. Okay, so this is what we have done for 1 permutation, and in total there are 6 permutations, so this will give me 6 terms like this one. This is known as the Leibnitz formula or the Laplace formula. Of course, it's not very useful or not useful at all for large matrices, but for matrices up to, well, 4, 5, 6, if there are lots of zeros, this formula can still be used, but of course it will not be our preferred formula. We'll prefer the pivot formula and the cofactor formula. Well, it's now time for the cofactor formula. So remember the formula for the determinant in the 3 by 3 case. It was given by this expression over here. So what we'll do is factor out the elements of the first row. So here A11, A12 and A13. If you factor them out, you obtain this expression here, and what is over here is the cofactor of this element. We'll denote it C11. This is the cofactor of A12. This is C12, and this is the cofactor here of A13. Okay, so you obtain this expression. So these elements over here are cofactors. They are computed from the determinant of the respective minors. So let us define a minor. A minor is constructed from the matrix A by drawing the corresponding row, row I, and the corresponding column, so column J. Okay, and the cofactor is computed by taking determinants of the corresponding minors. So this is C11, this is C12, and this is equal to C13. But you have to adapt the sign. If the sum of the indices is even, this is the case over here and over here, you have a plus. And if the sum of the indices is uneven, you have a minus. Okay, so this is how you compute the cofactors that are in here. So here we have used a formula that is expanded around the first row. We can also write the determinant expanded around the second row. So this will lead to A21 times the corresponding cofactor plus A22 times the corresponding cofactor plus A23 times the corresponding cofactor. Okay, so here we have expanded everything around row 2. You can even write determinants and expand things around columns. Let's do this around column 1. Then we'll have A11 times the corresponding cofactor plus A21 times the corresponding cofactor plus A31 times the corresponding cofactor. So here we have expanded things around column 1. So here we have the cofactor formula, but for an n by n matrix. So indeed you can work around rho I. Okay, we see that we work around rho I here because I is fixed. You've got it over here and you've got it over here. So you've got the sum of all the elements in the row times their respective cofactors. Okay, so this is the formula that is expanded around rho I, and as I've mentioned, you can expand down column J. So here J is fixed, and then you have to take all elements in column J times their cofactor and sum everything. Okay, so this will also lead to a valid computation of the determinant. And well, usually what you do is look at the matrix, see if there are a number of zeros in a particular row or column, and then take the corresponding formulation, okay, so that the computation is as easy as possible. And we had already talked about the cofactor. Okay, the cofactor is the determinant of the associated minor with correct sign. Okay, so the minor you throw out of the original matrix A, row I and column J, take the determinant, and then you have to correct for the sign. So if the sum of the indices is even, this will give a plus, and if it's uneven, it will give a minus sign. So here we talk about Cramer's rule, which is used to solve ax is equal to b when a is square and invertible. So Cramer's rule is obtained by rewriting this system ax is equal to b over here in another fashion. It's a times this matrix over here times this matrix over here, and this matrix we'll call b1. It's simply a where the first column has been replaced by b. Okay, and we see that this is indeed correct because what we have here, a times the first column is a times x, and this is indeed equal to b, and a times the second column will just select the second column of a. This is indeed the case, second column, and this one here will select the third column. Okay, so this equation is certainly true. So what we do now is use the formula determinant of ab is equal to the determinant of a times the determinant of b. You can easily see that the determinant of this matrix over here, since it is lower triangular, is the product of the diagonal elements, so it's x1. So we obtain this equation here, and this means that we can simply obtain the first element of x by taking the ratio of two determinants. The determinant of this matrix, remember that it's a with the first column replaced by b divided by the determinant of a. So this is the first component, and of course you can also obtain the component j, okay, by considering a matrix bj, okay, and there you have replaced in column a column j by b, okay, and you obtain this quantity over here. Well, so Cramer's rule says that if the matrix has an inverse, so if its determinant is different from 0, well, the system ax is equal to b can be solved by evaluating n plus 1 determinants. Okay, so remember that this matrix bj here has the jth column of a replaced by b. Well, the positive thing about Cramer's rule, and this is maybe why it's so well known, is that it gives you an explicit formula of the solution x. But in reality, it's not a good idea to solve the system of equation using this approach because from a computational point of view it is very heavy. So if you compare it with the method of using Gauss elimination followed by back substitution, it is very computationally intensive. Okay, so we can obtain an explicit formula of the inverse of a matrix that involves cofactors using Cramer's rule. Remember that we are looking for A minus 1 and A minus 1 such that A times A minus 1 is the identity matrix. Okay. So what we'll do is construct A minus 1 column by column. Okay, so here we construct the first column of A minus 1. So this means that A times the first column must be this vector over here. This is what we've written over here. And this is a matrix equation that we can solve using Cramer's rule. Okay, so we'll obtain first the entry 1, 1 of A minus 1. And this is simply the ratio of two determinants. At the denominator we have the determinant of A, and at the numerator we have the determinant of A, where the first column is replaced by this vector over here. So we can construct here the determinant over the first column. Okay, so it will be 1 times this determinant here. Okay, and you can see that this is indeed the cofactor 1, 1. Okay, so x11 entry 1, 1 of the inverse of A is cofactor 1, 1 divided by determinant of A. You can do something similar for the entries 2, 1 of A minus 1 and 3, 1. Okay, so we obtain something similar here, but at the numerator you obtain determinants where respectively the second column and then the third column have been replaced by this vector over here. Okay, so once again we can construct the calculation of the determinant using this column over here. So this will lead to this determinant, okay, with a correction of the sign here, because you're working around element 1, 2. Some of the indices is uneven, so we need a minus sign. But anyway, so this is the minor 1, 2. We have removed row 1, column 2. We have changed signs, but this is then the cofactor 1, 2. Okay, so notice that element 2, 1 of A minus 1 is constructed from the cofactor 1, 2 divided by the determinant. You can do something similar for entry 3, 1. So entry 3, 1 of the inverse of the matrix is the cofactor 1, 3. Notice that each time the order is reversed divided by the determinant of A. So we've just shown that element ij of the inverse of A is equal to the cofactor ji divided by the determinant of A. So this means that the matrix A minus 1 can be computed from the cofactor matrix transpose divided by the determinant of A. So see here, the cofactor matrix is a matrix with the elements which are the cofactors Cij, but you need to transpose here because element ij of the inverse relies on cofactor ji. So this is an explicit formula, and this is maybe why you see it so often in the literature, but this does not mean that you should use this formula for computation. Okay, remember that we don't use Cramer's rule to solve a system AX is equal to B, because it involves the computation of quite a lot of determinants. You'll have something similar for the computation of A minus 1. It is computationally heavy. What you should do is use the method that we have proposed earlier. We use the augmented system that you see over here. It's the matrix A with an identity matrix right next to it. We do Gauss-Jordan elimination and we obtain the following augmented system. Well, it's the identity matrix and you have the inverse of A right next to it. Okay, so this is good from a computational point of view, and it's good from a numerical point of view. So we'll do a few exercises. In the first exercise we'll compute the determinant of this matrix. There are of course several ways to do this, but the idea is of course to try to produce as many zeros as possible by doing row operations. And a row operation is, well, you subtract a row from another row, okay, and you could do the same things with columns over here. Okay, so it's not like in elimination when you have to work with row operations. Here you can also work with column operations. So what I'll do here is row 2 is equal to row 2 minus row 1. Okay, I could do row 3 is equal to row 3 minus row 1, but if I look at it, well, it's a bit annoying when you do this one here minus this one. Okay, so I would like to do row 3 is equal to row 3 minus row 2, because then I can factor out the n plus 2 and this looks a bit more advantageous. So of course I keep the first line, so I will have here 0, I will have a 1 over here, and I will have n plus 1, and then n plus 2 minus n, so this is 2 over here. Okay, and if I do now this row minus this row here, I have a 0, I've got a 1 over here, I can put the n plus 2 and factor it out. I will have n plus 3 minus n plus 1, so this will also give me a 2 over here. Okay, so what I will do now is obviously subtract row 2 from row 3, and this gives me this determinant 0, 1, n plus 1, 2, and we have a 0 over here, a 0 over here, and if I subtract these two I will have 2. Okay, so now we know that by the rules of the determinants, if you have a triangular matrix, well, then you simply have to take the product of the diagonal elements, so it's 2 over here. Okay, so when I do these types of exercises, probably it's good that you stop the video at the beginning of the example, that you first try to do it yourself, and then that you have a look at the solution. So here's the second exercise. As usual, we'll try by yourself first. So what I notice here is that A multiplies, it's a factor of the column here. It's the same thing for B and the same thing for C. So by the properties of linearity, you can write A, B, C, and we have factored out the A in this column, so it's AC, 1 and B. Here we have factored out the B, so it's BC, 1 and C, and here we have factored out the C, so it's CB, 1 and A. You also see that C over here, well, multiplies all elements of the row, so I can factor it out. So I've got A, B, C squared with this determinant over here, A, B, B, 1, 1, 1, B, C, A. So we're always used to work with rows. Okay, let's try something else and work with columns in this example and see that this is also working. So I'm going to replace column 1 by column 1 minus column 2. So this is going to lead to A minus B, 0, B minus C. I'm going to replace column 2 by column 2 minus column 3. So this leads to 0, 0, C minus A, B, 1, 1. And I can now, well, use this row over here to construct the determinant. Okay, so the minor that is being produced is the one that is shown over here. So this will be A, B, C squared times A minus B times C minus A. I'm now taking the determinant of that minor, and this one will give 0. Okay, but I have to correct for the sign, so it's minus 1. This one is in entry 2, column 3, so it's 5. Okay, so this is minus 1 over here. So we end up with this expression, and I can just rewrite this one as A minus C. Okay, so there are probably lots of ways of obtaining these results, but it's important to work a little bit with determinants, because we will see that we will need them in eigenvalue, eigenvector problems. Well, let's take this very simple example to apply the cofactor formula, and we'll apply it on row 1. Okay, so it's 2 times the cofactor of element 1, 1, so that's minus 1, index 1 plus 1, it's 2, and then I have to take the determinant of the minor, so that's 3, 3 minus 3 minus 2, okay, plus minus 3, and then I have to take the corresponding cofactor, it's minus 1. So the indices is 1, 2, so the sum of the indices is 3, and then the determinant of the corresponding minor. Okay, let's cross out row 1 and row 2, so you've got minus 6, 3, minus 2 and minus 2, and finally you've got minus 2. The cofactor is, well, minus 1, it's in position 1, 3, so the sum of the indices is 4 times the denominator of the minor, and it's minus 6 3 minus 2 minus 3. Okay, so this leaves us with 2 times. This is 1, this is minus 1, this is 1. So this determinant is minus 6 plus 9. So this leaves us plus 3. So we have 12 over here plus 6, and here we have minus 2 times 18 plus 6. So this leaves us with 6 plus 18 times 4, it's 54. 24 times 2 minus 48. Okay, 6 and 6, this leaves us with 12. Okay, so this is the value of the determinant. Well, what you could do is maybe compute the determinant, well, on the second row, third row, or on column 1, etc. Okay, as an exercise. But usually what you would do is maybe do a few operations on the rows or on the columns to produce a few zeros, and this is what I will illustrate now. We'll work on the rows, and remember, if I do this type of operations, right, a row minus another row, well, you don't change the value of the determinant. So what I will do is keep the first row, 2 minus 3 minus 2, will produce a 0 over here. So if I take the second row plus 3 times the first row, I produce a 0, and what I will produce over here is minus 6 minus 6. Will produce minus 3 over here. Well, for the third row, if I want to make a 0 over here, I simply have to add row 3 and row 1. So I have 0, minus 6, and minus 4. Okay, I can now have an additional 0 over here by subtracting row 2 from row 3. 2 minus 3 minus 2, 0 minus 6 minus 3. I will have a 0 over here, a 0 over here, and a minus 1 over here. And now things are easy because I have an upper triangular matrix, and the determinant is simply given by the product of the elements on the diagonal. Okay, and this also leads to 12. Okay, so you can see that if I do row operations, often the computations become a little bit lighter, and this might come in handy if you have to compute eigenvalues and eigenvectors of a matrix. Well, this is the same matrix than the one in the previous example, so we know that the determinant of that matrix is equal to 12. Okay, and let's assume that we want to compute the inverse of this matrix using the cofactor method. So we first have to determine the cofactor matrix. Okay, I'll do a few elements with you and then I'll put the rest, but you should of course try to do it by yourself. So element 1 1, I cross out this one, I cross out this one. The determinant is 3. I don't have to change signs, so this gives me a 3 over here. Next element over here, I cross out row 1 and column 2. I take the determinant that gives you 18, but it's element 1, 2. So I have to change the sign. So this leads to minus 18. And let's do another one. Element 1, 3 over here. So I cross out this one and this one. I compute the determinant. It's 24. I don't have to change signs. Okay, and if you continue, you'll end up with 0, minus 8, 12, minus 3, 6, minus 12. Okay, so the inverse of A, it's 1 over the determinant of A, and then you have to take the cofactor matrix, but you have to transpose it. So we have 1 over 12. We transpose this one, so we have 3, 0, minus 3, minus 18, minus 8, 6, 24, 12, and minus 12. So this leads to 1/4, minus 1 over 4, minus 3 over 2. So this leads to minus 2/3, a half, 2, 1, and minus 1. So what you should do, of course, is take this matrix and this one, and they should multiply to obtain the identity matrix. So you see that the computation of the inverse of a matrix, even in the 3 by 3 case, looks easy, but remember that there are already a lot of computations behind the computation of the determinant, and the cofactor matrix is also computationally intensive because it requires a lot of determinants. Let's compute the matrix inverse of A using the Gauss-Jordan elimination, and I've already put A in augmented form with the identity matrix right next to it. So let's start the procedure. So the first pivot is over here, and the idea is to create pivots just below. The multipliers will be minus 6 divided by 2, so minus 3. It's always entry divided by pivot, right? So it will be minus 1 over here. I can now copy the first row. It does not change. Obviously I will have zeros over here. Here I've got minus 6, minus 3. I've got 3 over here, 1 and 0. I've got minus 6 as well, minus 4. I've got a 1 over here, a 0, and a 1 over here. So the second pivot is minus 6 over here, so I need to create a 0 below. The multiplier is minus 6 divided by minus 6, it's a 1. Okay, well, to be correct I should swap those two, and the multiplier is 1. Okay, so let's do the computations. I can now copy the 2 first lines. Obviously I've got a 0 here and here. I've got a -1. We'll have -2, -1, and 1 over here. The pivots are given here in blue, and if you compute the product of these pivots, you see that you obtain the determinant. Okay, the matrix A is now in upper triangular form. These are the computations that we've done previously for the computation of the determinant of A. So now I need to produce zeros above the third pivot. So remember that now we start from right to left. And the multipliers are, well, entry divided by pivot, so it's a 3 and it's a 2 over here. So let's compute this. So now obviously rows 1 and 2 will change, and the third row I can just copy. So I have 2 over here, -3 over here. I'm creating a 0 over here. So here we'll produce a 5, a 2, and a -2. Here 0, -6. I'm producing a 0 over here. 9 over here, a 4 over here, and a -3 over here. And I can now copy the last line. Okay, so the pivots still the same. Let's continue and use the correct color, right? And I need now to construct a 0 above the second pivot, and the multiplier will be entry divided by pivot, so it's a half over here. And I obtain the following matrix. Well, obviously the 2 remains. I have got a 0 over here, a 0 over here. So now it's only the first row that will change. I will have a half over here, 0 minus a half, and I can copy the 2 remaining lines. Zero, 0, -1, -2, -1, 1. And still the pivots are the same. So I would like to produce here a identity matrix on the left. So I have to divide by 2. I have to divide by -6, and I have to divide by -1. Okay, so this will produce the following augmented system. I have now an identity matrix over here, and this means that on the right we'll have the inverse of the matrix, right? We know that from the theory. So we have 1/4 here, -1 over 4. We have -3 over 2, -2 over 3, a half, 2, 1, and -1. So let's check if this corresponds to what we had previously. This is indeed the case. So this matrix is the inverse of A, so it's A -1. So if you compare from a computational point of view, we'll see that you will do slightly less operations using Gauss-Jordan elimination, at least on this 3 by 3 example. But as the size of the matrix N increases, the advantage of using Gauss-Jordan elimination will increase, and then the other method, the cofactor method, will be actually unusable.